Uh, Good morning, everybody. Myself Swapnil Aswar. Today, I am going to give the seminar on the topic that is oil debris sensor. Today, we will see what is meant by oil debris sensor, what are its application, and where it is used. What is the working principle of this? What is the working principle of this sensor? Okay. At the end of this session, you people will be able to understand, will be able to answer this question. First of all, what is meant by debris? To whom should we call the debris? And then come to the point, what is meant by oil debris? Since we are dealing with the mechanical damages of the engine part, that is gear and the bearing, so we are concentrating on more on the oil debris. And then next, what is the need to measure the oil debris? Because unless and until we are having any kind of use to measure that debris quantity in the engine, we are not going for that process. So why to measure? What is the need for that oil debris measurement? Okay. Next is how to measure this oil debris. Obviously, question comes in mind: if we need to measure the oil debris, then what is the exact method to measure that oil debris? Then the device which is used to measure this oil debris, we called it as oil debris sensor. In this section, we will deal with what is the construction and what is the working principle of this oil debris sensor. And then what are the different pros and cons of the oil debris sensor? What are the advantages of this oil debris sensor, and what are the different disadvantages of this oil debris sensor? In this section we will see that. And after that, what are the application areas of the oil debris sensor? Where exactly we are using this oil debris sensor? What are the real-time example where this oil debris monitoring system are implemented in our day-to-day life? Generally, this is very important in the engines which are running very fast and which are running under the very high load and very high thrust. You take the example of fighter plane or advanced tactical fighter plane, which are used by the defense people, or the chopper, which are again used by the defense people, because this the engine of this aircraft and the helicopter tends to work under the heavy load, pressure, and again, if there is any damage in the engine component, then immediately we need to rectify that, because if we are not able to rectify that problem, then there will be the heavy loss, that is economic, as well as there will be a casualty, there will be we can lose the lives of the defense person. So we need to detect that problem, that our engine is going to fail, and if once we are able to find that it is going to fail, then we can immediately stop the working of that engine, and we can save the money as well as human life. That's all. And after that, if there is any alternative method for this oil debris measurement apart from this oil debris sensor, in which we are in this seminar we are seeing. Okay. Next, first of all, we will see what is meant by debris. The dictionary meaning says that it is the remains of something that has been destroyed or broken up. It is the remains of something that has been destroyed or broken up, or you say it is the wear and tear in the mechanical component. You can say the wear and tear of the mechanical component, or if I say the gear, then in case of gear, if the tooth of the gear is break, then that broken tooth, the particle, I can call the debris. That is, in geological, the debris usually applies the remains of the geological activity, like volcanic explosion, or you say landslide, whatever the things which are remain after this geological activity, you can commonly call it as the geological debris. In biology, you can say it is the dead cell or a fragmented of dead cell which is remain inside. You can call it as also the debris. Because in mechanical, we need to say that it is any broken piece of the working equipment inside the engine. So that is all about the debris. Now coming to the what is oil debris? Say we can say that what is oil debris? The mechanical component of the engine prone to work under the severe condition of load, pressure and the temperature. As we know that if I take the engine of this fighter plane, then obviously it is working under the high pressure, high temperature, high load, high thrust. Everything is very crucial, or the working condition is very critical. So under this condition, obviously the components of the engine tends to fail. See, if I am forced to work the gear or bearing of the engine under this tremendous condition, then it is obviously it can fail. So the wear and breakage of the component takes place, and this breakages of the component called as the oil debris, because these are breaking component and this comes in the oil sun. That's why this is called as the oil debris. Next. So what is the need? Then question, obviously the question comes in mind that what is the need to measure this oil debris? Because for this question you can answer like this: to detect the count of the failure of the to detect the count of the wear of the gear and bearing, you can say that this is the need for this oil debris measurement. Again, for the safety of this safety working of the engine, we need to find out the count of the oil debris. What is the exact amount of debris present in the oil? Because whatever the breakage particles of the gear and bearing inside the engine, that are all staying inside the lubricating oil. So that's why it is very important to measure this. And again, if our see, because we are using this sensor in the aircraft and or aeroplanes and fighter planes, helicopters, so it is very essential over there to continue monitor the engine health. What is the current status of our engine? If it oil debris level increases, means what? The wear and tear of this engine inside the engine is increases. So if it is goes beyond certain limits, then obviously the engine tends to fail. So we should at least able to find out that critical stage where the engine tends to fail, so that we can safely land the aircraft or helicopter, so that we cannot have any economic loss as well as human loss. So that is why what is the need for the measurement of this oil debris. Let's say consider the example of the aircraft engine F119 used in the advanced tactical fighter. Just we discussed here we are taken one example of the advanced fighter plane, that is F119. The engine delivered the thrust the 35,000 pounds, that is approximately equal to 160 Newton. This is approximately equal to 160 Newton. At this point, again this engine is designed for the supersonic flight without the use of afterburner. In this version, you are not using the afterburner, and again the F119 allows the sustained supersonic speed up to the Mach 1.72. Now you can understand what is the running condition of this engine, what are the various parameters affecting this engine. Under this condition, it is obviously your engine going to fail, so that we need to count that oil debris. So how to measure the oil debris? Okay. How to measure the oil debris? Now the question comes, how to measure this oil debris sensor? What are the different ways to measure this oil debris, and what are the different instruments we are having to measure this oil debris and from the oil engine? Next, the first one is the magnetic chip detector. This is and second one is the oil debris sensor, that is the inductive types. The magnetic chip sensor detector is the very old technique we are using since the initial stage of the oil detection. In this, only one magnetic device is used to detect the chip. This device is directly plugged into the oil line that is given to the engine. Inside that it is plugged, and with that magnetic chip detector, since it is magnetic, it attracts the oil, all the debris from the engine, and it measures the what are the debris present inside the engine, that is inside the oil. The next one is the oil debris sensor. That is it is inductive type because it works on the principle of induction. So we know that all we are familiar with this inductive principle. What is that? And next. First we will see what is the magnetic chip detector. See, this is the position exactly where it is placed. This is the oil flow inside the engine, and this is what the magnetic chip detector figure. We can see that it contains two magnetic element, and it is in place in between the oil flow, so that see, from here the oil is coming after it is flown through the engine, and it contains some ferrous particle, non-ferrous particle. When it passes through this magnetic chip detector, what are the total amount of ferrous particles which are present inside the oil, it get attracted toward this and it get hold over there, so that we can after it get attracted toward this, it stay over there as long as this magnetic chip detector is there. And once if we need to find when we are measuring this count of this debris, we simply will take out this magnetic chip detector and we count that what are the particles present inside that chip detector. See, this is the now we will see what is the working principle of that magnetic chip detector. As we know that it contains a pair of permanently magnetized electrodes separated by the small distance from each other. In previous slide, we can see that there is there is a magnetic element, a pair of magnetic elements. It is separated by some distance, and this is used to detect these oil debris, which are the ferrous material inside that we can detect by using that magnet. Thus, forming these two electrodes form the magnetic field outside that, and so that using this magnetic field, we can have the attraction of that oil debris and detection of that oil debris. Next. One of the electrode, out of these two electrodes, one of the electrode is grounded and the other is connected to the electrical wiring system using the capacitive self-feed. Out of these two electrodes, one electrode obviously it is grounded and the other is used for the detection of this oil debris, that is connected to the electrical wiring using capacitive circuit. That is for the measurement of oil debris. The capture of the metal debris is achieved using the magnetic field. As you know that there are two electrodes and it is forming the magnetic field inside that pipeline. So this magnetic field is the only way to detect that debris which are present inside the inside the flow of that oil. And then the magnetic plugs have to be removed and visually inspected to avoid the elaboration debris particle. What are the, if when we need to inspect that particle, we have to take out that plug and visually we have to inspect that what are the number of particles present over there. Next. Coming to the limitation of the magnetic chip detector, what are the different limitations of magnetic chip detector? First and major one is the detection efficiency of the chip detector is quite poor, because we see that it is placed, it is just deep inside that oil flow line, and due to that it is not occupying the entire area of that flow, so that there may be chances of escaping the ferrous material from that sensor chip detector. Again, the second reason is it is incapable of detecting the non-ferrous wear material. If the non-ferrous wear takes place inside the engine, then obviously it is only magnet. It is not going to attract the non-ferrous material which are present inside the oil. This is second disadvantage of this magnetic chip detector. And the third one is due to this, it is unable to detect the it falls all around due to the built up age of the fine ferrous material. If the fine ferrous debris come in there, and if it get attracted towards that chip detector, then obviously it gives a false indication that engine has got damage, the engine component gets damaged, and so it gives the false alarm to the engine driver or pilot. These are the limitation of the magnetic chip detector. Then what is the ferrous material? You know, all know that what is the ferrous material. If the material contains the iron as it constituent, then we called it as ferrous material. Since the magnetic chip detector only detects this ferrous material, it is used for that particular limitation. And why we are using this ferrous material inside the engine? The purpose is that because it has a high tensile strength, and it can sustain a heavy load and vibration, because our engine is going to work under the high tensile strength, and we need high tensile strength over there, and there are lots of vibrations and heavy loads are there. So we are using this ferrous material. Then what is non-ferrous material? In metallurgy, non-ferrous material means the material which does not contain the ions in particular amount. So these are the non-ferrous material. But though and the properties of this material is low weight, high conductivity, and non-magnetic. And due to this property, we are using this material also inside the engine. But the main disadvantage using this metal is that if the wear and tear takes place of this kind of material inside the engine, then our magnetic chip detector is not going to detect this compound failure. So that's why we are not using magnetic chip detector then come to the main point, oil debris sensor. We know at this time we are able to know what is meant by oil debris. So to measure this oil debris inside the engine, inside the oil, we are using the oil debris sensor. See, this is the construction of the oil debris sensor. It has it has three coils. There are this field coil and field coil. There are two field coils in this sensor and one sense coil. The entire oil which is inspected using this sensor is passed through this pipe. And this is the flow action. The oil debris sensor is the two-flow device which installed in the main oil supply and allows the entire flow to pass without obstruction. This sensor also called this the flow-through device, because whatever the amount of oil you are taking for the inspection, that all oil is passed through this sensor, through this tube. So this is called the through flow device. This entire quantity is oil is going to inspect in this device. So, and it is mounted on the main supply line of the oil pump. Okay, next. See, this is exact installation of the oil debris sensor. This is the outer part of the engine, and say this is the reservoir, and this is the main pipelining of this oil reservoir where our oil debris sensor is mounted. After that oil debris sensor, the vortex separator is mounted. The main function of this vortex separator is that it separated the oil debris, and again if any contamination is there, it also removes that vortex separator. The principle of that vortex separator is that it rotates the oil with high speed, and whatever the debris are present now, that is throw outside away the vortex. That is the working principle. After that, the signal conditioner is placed there. Whatever the signal we are getting using this oil debris sensor, it is sensed by the signal conditioner. It is then whatever the noise are present in that signal, it is removed over there, it is rectified over there in screw stage, and then it is given to the operator. That whatever then it feeds that data to the operator. What is the debris count in the engine, so that driver can say that this is the condition of the engine. The sensor incorporates a magnetic coil assembly which is capable of detecting and categorizing the wear metal particle by the size and shape. This kind of sensor is capable of finding the total count of the wear, which is debris which are present inside the oil, as well as not only it counts the total count of the debris inside the engine, it also counts what is the size of that debris, what is the quantity of magnetic, what is the quantity of ferrous material, and what are the quantity of non-ferrous debris present inside that oil. For the F119 application, the minimum size approximately are 125 microns for ferrous and 250 microns for the non-ferrous material. If we take the example of F119 aeroplane, then the least count of the minimum size of the debris that should be measured inside the oil is for ferrous it is 125 microns, and for non-ferrous particle it should be 250. Means oil debris sensor will count the debris about this particle size. Then the magnetic coil assembly consists of the three coil which is surrounded by the magnetically inner section. It consists of, you can see that there are three coils. This is field coil, sense coil, and again field coil. There are three field coils which are surrounded by the magnetically inner section. These are all surrounded on the magnetically inner section tubing from which our oil passes. So the two outside field coils are driven by the high frequency alternating current source. We can see that this is the field coil and this is the field coil. These two field coils are operated by the high frequency alternating current source. The high frequency alternating current source is provided to this two field coils, so that and again this field coils are the respective field are normally opposed or can cancel. The supply is given in such a way that they are cancelled with each other. This and this should cancel each other just inside this at this point particularly. The disturbance of the magnetic field caused by the passage of the particle result in the characteristic sense of the coil voltage. Say initially what we did, we managed the frequency of the both field coil. Then in this balance condition, if any particle, say magnetic particle or ferrous particle or non-ferrous particle, if it passes inside the tubing, then we get the fluctuating signal. That is, it says that there is a particle that is passed from the oil. The amplitude and phase of the output signature is used to identify the size and type of the particle. See, this is the signal which we get after the passage of the oil debris from the oil sensor. If the particle is the oil debris is the ferrous particle, then we will get this kind of phase. If it is the non-ferrous particle, then we will get the inverse of that phase. And the next, the phase of the signature depend on the nature of the passing particle. Obviously, if it is a ferrous material, it is upside down. If it is non-ferrous, then it will be the reverse. So that we can sense which kind of debris is present over there. The amplitude depends on the mass of the particle for the ferromagnetic material. The amplitude of this is dependent upon the mass for the particularly for ferromagnetic substance. And for the non-ferrous material, it is depend on the area. This amplitude for the non-ferrous material is totally depend on the area. If the area is greater, then the amplitude will be greater. If the area is small, the amplitude will be small. Whatever the signal we are getting from the oil debris sensor, it contains a very large amount of noise and other extra quantity of signal which we are not actually required for the monitoring. For that purpose, we are enhancing the signal collected by the oil debris sensor. Whatever the signal we are got from the oil debris sensor, we are going to purify that signal by enhancement. The oil conduction data is why we are rectifying that signal, because the oil condition data is the major source of information for the machine conditioning monitoring. Because it is the only source which we have for the monitoring of the oil debris inside the engine. It contains the information about metallic particle content, right? because whatever the signal we got, it is all about the whatever the debris which are present inside the engine. Thus reflect the level of wear and fatigue induced and the damage of the mechanical system. The signal indicate what is the damage takes place inside the engine. That's why we need to rectify that signal which we got from the oil debris. However, the signal measured through this oil debris sensor is severely tainted by the various noise. For example, the background noise present as well as the interference caused by the vibration of the structure where the sensor is mounted. Because see, sensor is mounted directly on the engine cover. Obviously, there are lots of vibration going over there, so that the vibration noise is there, and again there is a voice due to the wiring which is present in the entire assembly. So these are the two major causes of causes which interfere with the signal which we are getting from the oil debris sensor. This interference affects the performance of the health assessment unit considerably. Okay, because these are in very high quantity. This surely affects the signal which we get from the oil debris sensor. This will inevitably cause the misleading maintenance decision and hence the premature machine failure as well as the loss of productivity. If whatever the signal we get from the oil debris sensor, if we directly feed to the operator and we says if he read it directly, then surely he will take some wrong control decision, and surely he will take the premature assumption that the engine is failed right now, though the engine is working properly, because since there is lots of noise in the input signal, so the driver can't take the decision where the engine is running with smooth performance or the wear and tear takes place inside the engine. The enhancement of the signal is done in two-step denoising scheme. It is not done in one step since there are two interfering factor on the signal. Therefore, it is rectified in two steps. In first stage, the adaptive line enhancement is used. Technique is applied to remove the vibrational related information. Whatever the vibration related information that is get interfered with the oil debris sensor signal, that is taken, that is rectified with the use of adaptive line enhancement. And this partly once it is the adaptive line enhancement takes place, then that means the vibration related interference is taken place from the signal. Then this signal is then passed for the purification in the wavelet decomposition based denoising method, because there are some signals that is that are caused due to the wiring inside that sensor assembly. This interference is removed in this wavelet decomposition based on the denoising method. In this, after this method, you will get the pure form of signal whatever we require to monitor the engine assembly. Say, this is the original output of the oil debris sensor in response to the consecutive passage of the two particles without any interference. This is the standard waveform they are considering here. In this signal, they consider that there are two particles which are crossed from this oil debris sensor, and this is why we get the two peaks over here. And out of this, the sampling rate for this data collection is 8,000 Hertz. Out of this two particles, one particle is the ferrous particle and another is the non-ferrous particle. This is the pure form of signal, and this is not considered any kind of vibration, so it is the pure one. But in actual practice, what we get is this kind of signal we get from the oil debris sensor. See, here you can see that there is lots of noise out there, but at this point, the two particles are passed from the oil debris sensor. So we can't able to predict what is the quantity of oil debris passed from this by using this kind of signal. So that's why we are going for the signal rectification. In this signal, the background noise used due to the wiring and the measurement system also affect the performance of the system. In the case of very small particle, where the corresponding signature can be easily masked by the corrupting noise. First one is the adaptive line enhancement and its application in the vibration interference removal. In the signal conditioning, we will see the first step, that is the adaptive line enhancement. In this step, the filtering process is designed to eliminate the noise and of the component, and the pass of the signal component can be lead to an estimate of the signal corrupted by the noise. The filter can be either fixed or either adaptive. There are two kinds of filters which are used in this adaptive line enhancement. One is the fixed one, and second one is the adaptive. A fixed filter can be designed when the adequate prior knowledge about the both signal and the noise is available. If we know the, if we can consider what is the, if we know the whatever the amount of noise that probably can come with the signal, if we have knowledge of that noise, then we can use for the fixed filter. If it is not, then we can go for the adaptive filter. The adaptive one works on the adjusting the criteria parameter, adjusting certain parameter dynamically to compensate for the lack of such information. If we don't have the premature information of the noise signal, then we can have the adaptive filter, so that what is the importance of this adaptive filter is that it can adjust dynamically with the noise which is present in the signal. The frequency content of the particle signal are mainly depend on the speed in which the metallic particle pass through the sensor. We can see that it is a full flow oil debris sensor. Since whatever the quantity of debris that is present in the oil, that is all oil is passing through the oil debris sensor. That is it is monitoring the entire oil which is circulated to the engine. So the frequency content of the particle signal is mainly depend on the speed in which the metallic particle are passed through the sensor. This is associated with the lubricating oil flow speed. If the flow speed is high, then obviously whatever the signal we are getting, that is also fast. And if the frequency of the oil debris is greater, then again we will get the high frequency signal, and it indicates that there is lots of wear and tear occurs inside the engine. The vibration interference, on the other hand, depend on the vibration of the structure where the sensor is mounted. We know that the vibration is another cause which is interfering with the input signal of the oil debris sensor, and this vibration is caused due to the vibration of the engine, because oil debris sensor, it is placed on the engine, and engine is working on the various very high load temperature and all high thrust. Due to this, lots of vibration is going on there. If there is a mismatching of the gearing takes place inside the engine, there it again tends to lead a very high vibration. So this vibration is the main source of disturbance to the main signal which we got in the oil debris sensor. Accordingly, it is obvious that both signal and interference attributes are entirely depend on the working condition of the machinery and are unknown beforehand for the purpose of filter design, because this we can't predict what is the amount of vibration which the engine can produce, because our engine is not working at the fixed condition. It is working dynamically in the drastic conditions. So it is that vibration which are produced by the engine, it's again varying. So we can't assume that this much quantity of vibration it is induced in the signal. So we are unable to predict that signal also. Since the signal interference attributes are unknown, the adaptive filter we can use, because we know that simple fixed filter can't. If we have the premature data, then and only we can go for the fixed filter. But in this condition, we don't have the premature data of the vibration, so we are going for the adaptive filter, because it can adjust dynamically. So that's why we are going for the adaptive filter. The adaptive system is capable of adjusting the filter parameters according to the working condition of the machinery. If the vibration is high or low, whatever may be, our filter will adjust with that vibration. So that's why we are using this fixed filter over here. So sorry, that's why we are using the adaptive filter. This is the adaptive line enhancement technique. How we are removing the vibration signal from our main signal, which we are getting from the oil debris sensor. See, this is the input signal which we are getting from the oil debris sensor. We are giving this to this adaptive line enhancement. In this, what it is done, we are considering the one reference signal. Actually, this is the reference signal, but in the adaptive line enhancement technique, whatever the signal we are getting, from that signal only we are taking the reference signal. Just only what we are giving some delay to that signal, and again after giving that delay, we are again combining that two signal, and in this combination process, what we are doing, we are removing whatever the vibrational noise present in that signal from the total signal what we are getting from the oil debris sensor. Here we are removing that, we are negative side indicate what we are removing that vibrational signal from the main signal, and thus we are getting the output signal that contain no vibration interference. That's how we eliminate the vibrations from the signal. Next, second method is the Vellore decomposition based on the denoising. Whatever the signal we are getting from the ALE, adaptive line enhancement technique, it contains the Gaussian error. Adaptive line enhancement method is unable to remove that Gaussian background noise. So for that purpose, we are going for the Vellore decomposition noise based denoising technique. In this technique, we are removing the whatever the remaining losses, that is Gaussian losses. That is Gaussian background noise. Gaussian noises we are removing in this method to further enhance the signal achieved through the ALE setup. A Vellore threshold denoising scheme is proposed. The Vellore transformation is given by this equation. That is f of psi of 2 to the power minus j t n minus 1 is equal to 1 by root 2 j integration minus infinity to infinity f of t psi of 2 to the power j t n minus 1 dt, where m is not equal to m or j is not equal to k. The orthogonal of this Vellore transformation is given by this equation. That is f. This function is equal to, is the function of summation of f of psi of jn into psi of jn, and where this is the psi of jn is this function. In the presence of noise, this approach is equivalent to the hard threshold denoising method. The thresholding function is defined as theta t of x is equal to x if mod of x is greater than or equal to t. Theta t of x is equal to 0 if mod of x is less than t, where x is the Vellore coefficient and t is the threshold value. Next, we have this f function, that is the Gaussian function, and where z is equal to f plus w, where w is the white Gaussian lash. Now one can easily see from this equation, in this approach the Vellore coefficient is larger than the some threshold value are used for the reconstruction of the process, and the reset of the coefficient the rest of the coefficient are very small. For this, in this equation, this w, that is Gaussian coefficient, is very small, so one can neglect that, and in this way we can remove that noise, Gaussian noise, by this technique. See, this is the measured signal from the oil debris sensor, and this is what exactly the signal what we get from the oil debris sensor in the current working condition. And the sampling rate, again, it is 8000 hertz. Next, then the interference removal result obtained after the ALE. Once adaptive line enhancement is done, then this signal gets somewhat rectified, and you can see this is the rectified signal, means it contains less noise than the previous one. So in this case, whatever the vibrational noise that is present inside the signal, that is totally eliminated. The only noise remaining is the Gaussian noise which we are eliminating in the next step. See, this is the result obtained after the threshold denoising after the ALD output. Whatever the signal we are getting in the ALD, that we feed to the threshold denoising, and in this the Gaussian noise are removed completely, and after that we will get the clear cut signal which does not contain any kind of noise. And see, the oil debris sensor, generally why we are using this sensor. Oil debris sensor are generally used to monitor the failure of, first one is the bearing and oil, second is the gear, because these are the two components which work under the load inside the engine, because these are the only working part inside the engine which work under the severe condition of temperature, load, pressure, and so many other. Next. See, this is the wind turbine planetary bearing. These are the bearing and gears of the wind turbine. See, there is a wear and tear takes place in the planetary bearing gear, and again the tip of the gear inside the wind turbine also get wear and tear. To monitor the status of this bearing and all gear, we can use the oil debris sensor inside the wind turbine also, because oil debris sensor, it detects the amount of debris, that is what is the wear and tear takes place inside the gearbox of the any engine, that is count, and it clearly indicates that the engine is going to fail. If the count of that oil debris reach to certain level, then it indicates that your engine is going to fail. At that stage, we can stop the working of that engine, and we can replace the gear or whatever the bearing, whatever the component which is damaged inside the engine, so that it can help to monitor the engine performance. Next, this is the oil debris monitoring result for the wind bearing. This is the test which is carried on the bearing of the wind bearing. This is the on y-axis they plotted the number of particles which is counted by the oil debris sensor, and this is the time elapsed. As the time elapsed, the number of particles which are getting sensed by the oil debris sensor get increases. At 0 time it is 0, 0. As the time increases, the count for the debris, that is wear and tear inside the engine, get increases. This is all about this. This is another application of this oil debris sensor where it is used in service aircraft oil debris application. It is used in F-22 Raptor. That is it is again fighter plane. It contains the F-119 engine. Inside that F-119 engine, the oil debris sensor is fixed, so that it can maintain the oil debris content, and so that it can monitor the health of that engine. Again, it is used in joint strike fighter. In that plane, F-315 engine is placed inside that engine. It is used. Again, it is used in Eurofighter, Typhoon, and Seeking helicopter. Again, next. So this is all about what is meant by oil debris, how to measure oil debris, and what are the different kind of application of oil debris sensor. Now we will see one. Now come to the oil debris monitoring technology for the aircraft. We will take one case study where the oil debris monitoring sensor is used. We will consider the example of aircraft in which the oil debris sensor is mounted. At this stage, we know why to monitor the oil debris. First, to check out the engine wear and to predict the engine failure. First, engine wear means the wear of the gear bearing inside the engine, that is the engine failure, engine wear here it means, and to predict the engine failure. If the engine wear is high, then obviously it is going to fail the engine. So to predict this, we are going to monitor, we are going for this oil debris sensor. This is the bearing gear life cycle tested using the oil debris sensor. In the initial stage, when you install the bearing or gear, the initial wear particles are several hundred micron in size. Initially, the debris size is in micron, and it again in the running time it comes down. When it actually it is in a normal operating period, the normal operating stage, this is the normal operating stage of your gear or bearing inside that engine of the aircraft. The debris generation reaches to the low rate, that is in equilibrium. This is where our engine was without any defect. Next. In the stage 3, see, this is the primary wear stage and this is the secondary wear. In this stage, what happens? The debris, whatever the debris count goes continuously increasing, and at this stage, when debris count reaches to this particular stage, we assume that the engine component is failed. That is the gear or the bearing which is placed inside, working inside the engine is failed. Next. See, you can see the picture of this extruded rolling contact fatigue, and this is the RCF particle, that is the oil debris inside the engine. Next. This is the product evaluation of this. Actually, this is the how this oil debris sensor evolved. Initially, the magnetic plug was used to measure the oil debris only. It is very simple, inexpensive, threaded in design, and what is the main disadvantage using this is there is a oil loss when inspection, because we have to take out the sensor every time from the oil line, and we need to count the debris manually. So that is during this operation there is a oil loss takes place, and again it is a labor intensive. You have to give them lots of labor, and you have to work manually over there. So we are not using this magnetic plug. Then coming to the chip collector, again it is relatively simple, again inexpensive, threaded or quick disconnect and design. One of the advantage over the previous one is that there is no oil loss in this, because it is threaded in quick to disconnect and to engage, so that there is no oil loss here, and again it is very easy to inspect using this. Then electronics chip detector comes in picture. It alerts the crew when the debris is captured. It is the automated kind of sensor which detects once the debris is detected, it directly alerts to the crew which is working on the engine. And for this purpose, the wiring is required, because it uses the electronic circuit. The wiring is required. These are the price advantage for the oil debris monitoring. For this to drive the oil debris monitoring, it should be reliable, it should be commercial, and it should be very easy. Some requirement for the advanced debris monitoring system is given here. The failure detection reliability. It should detect the failure. It should detect the oil debris produced inside the engine at the very short duration of time. Means, if the debris is produced, it should directly count the oil debris. It should provide the verification process to support the maintenance decision. Again, it should be very quick, responsive, and it should be communicative with this control unit of this aircraft. Next. Now coming to the quantitative debris monitoring technology, and this we will see how the aircraft engine is monitored for the oil debris depending upon the quantities of the debris presented inside the engine. This is the Boeing 777. This is the passenger plane. On this quantitative oil debris monitoring system is mounted. This is the first commercial aircraft engine with advanced oil debris monitoring system, and It has completed over the 7 million engine flights over since 1995. The debris monitoring systems hardware. These are the different hardware which is present inside the oil debris sensor, which is mounted on that Boeing 777, that is the aircraft. It contains a 3-phase vortex separator and air and debris oil form. This contains the 3-phase vortex separator, which removes the debris and air and any other particulate present inside the oil. Again, it contains the signal conditioner, which conditions the signal which got from the oil debris sensor, and the quantitative oil debris monitoring sensor, which is the oil debris monitoring sensor. This is the exact location of the oil debris monitoring system. This is the outer cover of that engine on which this entire system is mounted. You can see this is the oil reservoir upon which the oil debris sensor is mounted, and this is connected to the vortex separator, and after that it is again connected to the signal conditioner. This is the inside of the 3-phase vortex separator. This shows that how exactly the air 3-phase vortex separator works. You can see that from upper side the air, oil and debris come in the 3-phase vortex separator, and it gets swirled due to it gets swinging motion, and due to that whatever the debris present inside that oil it removed, and the remaining oil which is and is passed for the further separation. In this, the debris separation efficiency for this oil, the 3-phase vortex is 75 to 95%, and the air separation efficiency is up to 95%, greater than 95%, and the oil separation efficiency is 99.8%. This is the quantitative oil debris monitoring. How this sensor is work, we have already seen that these are the chips and these are the coil assembly, and we know that how this works. Next, this is the performance QDM system performance. It counts the ferromagnetic particles that exceed the mass of 50 μg, that is and equivalent to 230 micrometer diameter spherical. Means whatever the count we are getting above this measure, that is 230 micrometer, that count only we are getting. And for the inductive sensor, the sensitivity is the function of mass particle mass. Next, this is the entire system of the quantitative oil debris monitoring. In this, here we are getting the counting the oil debris, and whatever the count that is converted into the signal. That signal is then given to the QDM signal conditioner, and this signal conditioner limits then that whatever the rectified signal which we are getting, then it is supplied to the control unit. Next, this is the QDM signal conditioner. This is the inside of this QDM signal conditioner. This is the alert algorithm and maintenance procedure for this QDM. These are the only steps which follow during the working of the QDM. This is the exact picture what happens in the QDM. Here is our oil debris sensor. It counts the oil debris above the threshold frequency. Means if the count is threshold level is 230 micron, then it counts the oil debris above that level only, and then this whatever the signal it generated, it passes to the signal conditioner. Signal conditioner conditions the signal, removes the unwanted noise, that is vibrational noise and Gaussian noise present in the signal. That then rectified signal, that is pure signal, is then passed to given to the FADEC, that is fully authoritative digital engine control, which is present inside the aircraft, and this from this then it is given to the ACMF, that is aircraft condition monitoring system, and from there you can control what is the exact condition of your engine, where the engine is working properly or it has got damage. From there you can monitor the engine condition. This is the maintenance access terminal in the 777 flight, that is Boeing 777. From here you can monitor the your device level. Means you can say that your condition of the engine. And this is the display of the EICS display on the 777 flight deck. This is the QDM sensor for the smaller engine. Up till now, what we seen is for the aircraft, and these are the different types of sensor which are used for the smaller engine. QDM, continue. It indicates the ferromagnetic chip with the mass above the present threshold. You know that we set some threshold value, and our QDM detects the debris above that preset threshold value, not below that value. The mass threshold is set so that the environmental noise does not cause the false count. It is set in such a way that set in such a way that it should not mess with the oil environmental noise. The sensor collects and retains all chips for the alert verification. This is all about the working again of the oil debris sensor. Next. The simplest form has very simple electronics and no software. It does not have any software included unless and until we are going for the very fine debris count. Generally, software is not used in this sensor. And conclusion. Then we can say that the QDM is proven mature system for the all kind of aircraft, helicopter, fighter planes, jets, and all engines where it tends to have working very drastic environmental condition. That we can use the oil debris sensor to monitor the engine condition, and that's all. Thank you.